Hi, let us start with Max class 4 and let us have a concept building session on basics of calculus. So first thing we are going to discuss in calculus is what do we mean by a function, and extend the concepts of calculus and understand what do we mean by limits, continuity, then go on to differentiation. So let us see what do we mean by each and every term written here. First thing, function. What is a function? Function is nothing but a relation. What relation? Relation between dependent and independent variables. Say for example, I say y equal to f of x. X, here we see that x is describing y. Y cannot take any values it needs. Y will be able to take the values decided by x. And what value? That will be decided by the function. Correct? That will be decided by the function. So, it's something like we are putting a constraint on y, that you can take these values only. So, y is dependent on x and x is independent. What do I mean by this? Say for example, let me take a function for example. Say x is here, y is here. X can take any value. Let me take a function like this. Here x can take any value, but y cannot take any value. The values of y are decided by x, and it cannot take any value. It cannot occupy any value here. It can occupy only the values here, correct, on this function. So x can take any value here, whereas y cannot take any value here. This is not possible. So we say y as dependent and x as independent. That is, it has the freedom to select any value it wants, whereas y will be limited by x. Fine. Now let us extend this idea and understand what do we mean by limits and what are the special cases we will see different functions. First thing, it all started like this. We want to predict the value taken by a function. So what do we mean? Say for example, I have a graph of a function y equal to f of x, and it looks like this. It looks like this. This is the function. From the function we observe that if I have to say let me say this point, as x equal to a, I am interested in predicting what is y at x equal to a. I am interested in predicting this value. So what I can say is, if I know a value very close to a, if I know a value very close to a, something here, these are x, this region and this region are having x which are very close to a. That is, for example, say I want to know what is y at x equal to 2. Say that I know y, I already know, this is what I have to know, this is what I want to know. What is y at x equal to 2? Let us say that I know what is y at x equal to, say 1.9, 1.99, 2.02, 2.2, like this. I know the values of y at these points. I know the y's at these area points. Now x equal to 2 lies somewhere in this area, correct? So from this, by knowing all these values, I can predict what is y at x equal to 2. I can predict. I can say that there is a tendency when I go from here and when I come from here, I almost reach the same value at this point. So from this I can say that y, the value of y at x equal to 2 will be predicted by knowing values of y at x equal to 1.9, 1.99, 2.02, 2.2, like this. Now observe, I have very cleverly chosen these values. In this 1.9 and 1.99, 2 is somewhere here. I am traveling towards 2 in one direction, whereas here I am traveling towards 2 in this direction. So what I am trying to say is, the value taken by the function, say it closes on to 2 here. Say for example, here in this graph I travel like this, I travel like this, and I tend to close at this point. So the value of y at x equal to 2 closes at this point. It is converging at this point. It is something like, say, to put it in a very convenient easy way, you come from a second, say this is a building, this is first floor, this is ground floor, this is second floor. You come from second floor, you go from ground floor, you converge at first floor, correct? So like that we travel from this and we travel from here, we hit this point. So it was decided that limit, mathematically I am now writing this, limit x tends to a, f of x is equal to f of a. That is, as x approaches a, f of x takes the value f of a. So let me capture the same diagram again here. The diagram what I drew previously. I took a function like this. This is y equal to f of x let's say y equal to f of x and this is x. So what happens is we were trying to find the value at x equal to a. X equal to a, and we said that the value converges at this point. Correct? Now the question now comes, we have defined this limit x tends to a, f of x is equal to f of a. Now the question asked is this true always? Basically, let us ask this question again and again in maths to understand many concepts. Is this true always? The answer is a very big no. This need not happen always. Now let us see some cases. Let us see some cases to understand why is this no. Now the moment I have said no, we should understand why it is no. Okay. Now let us see few cases. And first thing, let us define as a requirement, we will define what do we mean by left hand limit and right hand limit. In seeing the previous example, we say that I am taking the same example. By knowing y, by finding y at x equal to 1.9, 1.99, 2.02, 2.2, we can predict y at x equal to 2. Now x equal to 2 lies here. In this region we are traveling 2 by taking values less than 2 here. That is 1.9, 1.99, 1.999 like that. Here we are taking always values greater than 2 and we are reducing the values and we are converging towards 2. This is greater than 2 always. That is, we are coming from 2.3, 2.2, 2.1, 2.01, 2.001 like that. We are approaching towards 2. So here it is always greater than 2. So I will say that as this is 2 plus region. And this is always less than 2, so I will call this as 2 minus region. So in this region we are approaching 2 from the left and here we are approaching 2 from the right. So this region is called the limit. The 2 plus side is called the right side and the 2 minus side is called the left side. Now if 2 is a number which we have taken for an example, now if I replace this with a general number a, that means it is a minus and a plus. So when I approach a in this direction, this is called left, and this side it's right. Okay. Now let us go back to the question we asked. Why is it is not true always? And we will see the cases. Let us see our case 1. Let me take a f of x which looks like this. Now here let me say this is the point x equal to a. Now let me do what I did in the previous function. Let me try to approach x equal to a from this side, and let me try to approach x equal to a from this side. When I approach from a plus side, I hit this value, and when I approach from a minus side, I am hitting this value. Observe that these two values are not same. Please observe this. This is very important. That is, in this example we saw that the values when I travel this side and this side are meeting the same point, whereas in this example when I travel this side and when I travel this side, I hit different values. Okay. Now let us keep this as observation and go and see case 2. Let me take a function g of x, some g of x, which is defined like this. That is, it always follows this pattern, but only at a particular value it fails to follow this pattern and it takes a different value. So we have a short spike here. Short spike. We have a short spike in the function. This is happening only at a. Please remember, this function is such that spike exists only at x equal to a. That is, g of x everywhere is same, whereas it is taking some value at a, some value at x equal to a. Rest every, apart from x not equal to a, x not equal to a, it follows a pattern. Okay, let me rewrite this part alone. It is not clear. Well, I am rewriting the last part alone. What I was saying was g of x. I am describing the function in a language, English language. This follows pattern x not equal to a, deviates pattern at x equal to a. That is, it looks like this. The whole function is following this pattern only at x equal to a, we have a spike. This is x. So what do we conclude? This is our case 2. So from K, what is the conclusion of case 2? Now let us approach x equal to a in this direction. Let us approach x equal to a in this direction, that is in the region a minus and a plus. Let us approach x equal to a. Observe that these two values are converging to this and this, which are close. That means when we travel from a plus to a or a minus to a, the values taken by g of x converges. We are approaching the same value here, but what is the deviation? But the value of g of x at x equal to a is different value that is convergent value is not equal to value taken by f of x at x equal to a. So this is the conclusion of case 2. So basically we started with a function and we saw some special cases, and we now we have some concluding remarks. So from this, let us define what does a limit means, and more importantly, we will define the idea of continuity. So first thing we will like to, from case 1, we conclude limit can predict the value taken by function only when right and left value converges. That is, this was our case 2 case, right? This was our case 1. We were getting different values when we travel like this and like this. We were hitting different values. Right? So limit x, let me write this here, limit x tends to a minus should be equal to limit x tends to a plus. that is limit x tends to a minus f of x should be equal to limit x tends to a plus f of x. If this condition is met, we call continuity. No, this is incomplete. Why? Because we have case 2. We have to take the remarks from case 2. We have not taken that, right? So let us redefine continuity with the understanding from case 2. What does our case 2 says? Case 2 says that it is not sufficient limit x tends to a minus f of x is equal to limit x tends to a plus f of x. This is true in case 2. This property is obeyed. But what happened? This value was not equal to f of a. So we define continuity as limit x tends to a minus f of x should be equal to limit x tends to a plus f of x should be equal to f of a. If all this is a complete. Now this is complete in all aspect. So this is the conditions for continuity. Okay, having seen this, let us proceed towards understanding differentiation. We are going to see the birth of differentiation rather. Now let us, for example, take a function Now let us take a function f of x. Let me take 2 points. Say A and B. Okay. Now there exists some other function like this. G of x, which happens to take the same values at a and b. That is f of x equal to g of x at x equal to a and x equal to b. Okay. Now, what do we mean by this? Say for example, suppose if I do f of b minus f of a by b minus a. What does this mean? I am taking this value, I am subtracting it with this value, and then I am doing a subtraction here also. What does this give me? This will give me a an average change in f of x. Correct? Now this is same as g of b minus g of a by b minus a also. Because of this g of a and g of b are same as f of b and f of a, so this will also be same. That means average change in interval a comma b is same for f of x and g of x. So though f of x is not same as g of x, they are totally two different functions, but still their average rates are same. Their average rates in this interval is same. So this average change is not so useful in analyzing f of x because it is not unique. Average change is not unique to f of x. Please remember this. Okay. So what happened? We want to analyze a change which is so unique to f of x. The requirement is we want to find a change in f of x which is unique to f of x. So what happened? Okay, they told okay, let us not take a and b, let us take some other interval c, ac. Now what happens? They want to do f of c minus f of a by c minus a. This is what they want to do. But what happened? Some fellow came and constructed another function like this. Some fellow came and constructed another function like this, the one which I am drawing by the thickened line. Again what happened? Same problem repeats. Again f of, let me call this function, new function, as some p of x. Again the same problem repeats. Correct? What happened? P of c is same as f of c, p of a is same as f of a. So f of c minus f of a by c minus a, this value will be same as p of c minus p of a by c minus a. Again this is not a unique change. So we were trying to find a change in y and that is change in f of x, which will be, we are basically trying to find a change change in f of x which will describe its behavior. So we started with a f of x like this. We took 2 points A and took 2 B. This was f of x. correct? Then what we had another function g of x like this, which almost take the same value at a and b. This is g of x, and we found that g of b minus g of a by b minus a is equal to f of b minus f of a by b minus a. So we took another point C, but what happened, one more fellow came and constructed a function like this called p of x, such that p of c minus p of a by c minus a is equal to f of c minus f of a by c minus a. Again, in interval AC, I am unable to find an unique change in f of x. Again, I am back to the square one. The same problem is persisting. So, same problem continues. Then, okay, let us from C, let us come to another point called D. Let us call a point D here, and let us try to find another function. Let me try to analyze f of x in a comma d. The moment I select D, one more fellow comes and says that no, see, I am constructing another function like this. Let me call this as some k of x. Again, what happened? K of d minus k of a by d minus a is equal to f of d minus f of a by d minus a, which again points to the same situation. We have not progressed anymore. So what to do? Finally our fellow came and told, okay, let us find, I will find a point so close to A which is almost separated by 0 distance. It is almost close. I am taking a point, take a point so close to A, such that the point converges to A. Now, when I take a point so close to A, we cannot plot any other function like this, and the game stops there. So, I can define a change in x which is unique. Such a change in x will become like f of a plus h minus f of a by a plus h minus a. This will simplify to f of a plus h minus f of a by h, where h is the separation between the point and A. So how we have taken? It is so close to A. That means limit h tends to 0. limit h tends to 0, I am finding a variation in f, that is infinitesimally small change in f of x is what I am finding.